Yes, welcome students. This time I want to share one more lecture. It's for the students who are pursuing lectures on Riemann integration. Riemann integration में मैंने आपको तकरीबन 11 लेक्चर्स दिए हैं, तो ये तो थोड़ा आस्ता आस्ता मैं चल रहा हूँ, तो इसलिए it will take some more lectures this on Riemann integration. तो मैं ये थर्म स्टेट कर रहा हूँ. इससे पहले मैंने आपके साथ डिस्कस किया था, क्या इसका नाम है, लोअर सम एंड अपर सम क्या है. लोअर सम और अपर सम आपको फुल्ली, मुझे लग रहा है कि अब आपको समझ आया होगा, लोअर सम अपर सम. तो उसके बेस पे हमें एक थर्म है, कभी इसको लिखते हैं फर्स्ट लॉ ऑफ मीन भी. वहाँ इस तरह नहीं थर्म होगा स्टेट एंड प्रूफ फर्स्ट लॉ ऑफ मीन, तो हो भी सकता है लेकिन कम चांसेस है थर्म को इस तरह आना फर्स्ट लॉ ऑफ मीन. ये मैंने आपको थोड़ा जस्ट आइडिया दिया है, बिकॉज सम ऑथर्स राइट इन दिस इज द फर्स्ट लॉ ऑफ मीन इन दिस रीमान इंटीग्रेशन. स्टेट में कर रहा हूँ. इट इज इफ एफ एक्स is a real valued bounded function defined on this closed interval, defined on the closed interval AB, small m and capital M. This is the infimum, which is also called GLB, and this is the supremum, which is also called LUB of this function f on this closed interval AB. Then this condition will hold. Small m times b minus a is less or equal to LPF. It means lower Riemann sum on any partition. Yes, I have not mentioned P. P is any partition. P being any partition. It is any partition on closed interval AB. You may pose a question here, where does this P come from? P is any partition. You may take partition P1, P2, P3, whatever you like. It is any partition on the closed interval AB. Then this is the lower Riemann sum on this partition. This is the upper Riemann sum on this partition. And this is less or equal to m times b minus a. अगर आप इसको माइन्यूटली थोड़ा देखेंगे, अपने मैथमेटिकल ऑब्जर्वेशन से आप इस थर्म को देखेंगे, ये जो हमने लिखा LPF, P is not a particular partition. You can take any partition, P1, P2, P3, P4, whatever the partition, infinite number of partitions on the closed interval AB. आप देख रहे हैं कि ये lower Riemann sum, set of lower Riemann sum and set of upper Riemann sums, they are caught between this and this. Small m times b minus a and capital M times b minus a means this remains there, the GLB, and that remains LUB. So we say that the set of lower Riemann sums and the set of upper Riemann sums lie between. They have a boundary, minimum boundary and maximum boundary. So we say lower Riemann sums, set of lower Riemann sums and set of upper Riemann sums, they are itself bounded. When a function is bounded on the closed interval AB and we take any partition, then that partition, the Riemann sum on that partition and upper Riemann sum on that partition also remains bounded. This is a very important, interesting thing that which we'll be using in Riemann integration. When we take lower Riemann integration and upper Riemann integration, there I will just mention you this term there. Remember this, very important result. I will be mentioning this once again and again. Let us see the proof. Proof is very simple. You see, this is proof. How proof will go. You are given that, it is given that small m and capital M being GLB, greatest lower bound, this, and LUB of fx in closed interval AB. This is the LUB and GLB of this. This implies that M is less or equal to fx, is less or equal to capital M for every x belonging to closed interval AB. Whatever value you give to x, our fx is caught between small m and capital M, because they are bounded. They have the LUB, GLB, lower bound, upper bound. So we take this as the GLB and this as the LUB by the given condition. This is the condition. Now we start like this. We write let P be any partition. Partition I have defined. Go to previous lectures. Do not jump over this lecture number 12 immediately, please. You will get confusion. You will leave it immediately. When you immediately jump over this lecture number 12, then you will leave it immediately until you have some notion about partition. You have the notion about what is the lower bound, upper bound, then LUB and GLB. I have discussed all these in from lecture number 3 onwards up to lecture number 9 or 10. You should revise them. Then it will become very simple to you. You will not pose a question here. How where P comes? What is this? What is LPF? What is UPF? You don't need to ask these questions when you revise the previous lectures. Note it. So we take let P be any partition of closed interval AD. We take P as x0 as usual, x1, x2, x3. This is xr minus 1 general I take between this xr, or you may take xi minus 1 xi, no problem. Then this is xn. What is this here? It is your first point of the closed interval. This is your A. We start from this A, and this is, we rename B as xn. It is just rename. We rename A as x0 and we rename B as xn. So what is the relation between these? This is x0 is less than x1 is less than x2 is less than so on to these are less than xr minus 1 less than xr. This is less than xn. This is the relation. Now this closed interval on the basis of this partition will have many sub-intervals. If you have this n sub-int, I have told you there how many this you take, how many sub-intervals will exist, that I have mentioned in previous lectures. So this implies, since f being bounded on closed interval AB, implies f remains bounded on each subinterval, on each subinterval of closed interval AB. Whatever you take subinterval, you may take a subinterval. This is also a subinterval xr minus 1 xr. You may take x2, x3. You may take x1, x0 as a subinterval of this interval, because this partition gives rise to the subintervals, which are known as the segments of the partition. I have discussed it previously. Okay, so I take a subinterval, this xr minus 1 xr. So this our f will also have a lower bound and upper bound, because it remains bounded on each subinterval. I1 you may take subinterval, I2, let it take general subinterval IR. It will be bounded on this subinterval also, means it will have a there what is called this LUB and GLB. It will have LUB and GLB there, and we will develop a relation between this M, small m, capital M, and the LUB and GLB of f on this xr minus 1 xr. Then directly you will get this relation. Just wait, I will go to drop it. Yes, we said that f is, this implies that our fx is also bounded. It remains bounded on subinterval IR is equal to xr minus 1 xr for any r you will get these subintervals from this I1, I2, I3. So when it is bounded on what is called a closed interval AB, you take a segments of that closed interval by the partition, so it also remains this bounded on each subinterval. So we write now, let small mr and capital MR be GLB, that is infimum and supremum of F on IR on this closed interval. This obviously means that your MR is less or equal to capital MR. Relation between the GLB and LUB, because this is the GLB, this is the LUB of F on the same subinterval. Let this be second equation. You see, situation is like this. You may understand the situation. This is your closed interval A, B. On this you take one subinterval. This is XR minus 1, XR. Here you have, say, M GLB. You already have capital M LUB on whole interval. In this interval you have small mr, and here you have capital MR on this interval. Just to see what happens. We want to develop the relation. It is obvious that this is less than this, is less than this, is less than this, and this is greater than all, because it is the LUB on whole. Capital M is the LUB, least upper bound of F on the whole interval, and small m is the GLB of F on the whole interval. So this will be the minimum of all, and this will be the maximum of all, and this subinterval lies on this. Let us develop a relation. You see, since our closed interval, subinterval XR minus 1, XR is subset of what? AB. It is a subset of AB. Now, what is MR? Now, small mr, that is actually infimum offset of Fx it is the infimum offset Fx such that x is greater or equal to XR minus 1, less or equal to XR. So small mr is the infimum of Fx on this interval, and we said this is contained in this. What happens? And this mr, just look there, this is greater, this is less. When we compare the infimum on the whole and infimum on the subinterval, the relation between this and this is less than this, because this lies on the right of M. It cannot go on the left of M. So we say this MR is, this is what? This is actually greater or equal to infimum of Fx such that x is greater or equal to A, less or equal to B. Very important. When we compare the GLB on the whole and GLB on the partition, the situation is this: the GLB of a subinterval lies in between A and B. So GLB of this, it is on the left. So we say that this will be less than or equal to this. It is the obvious condition. So our MR here, MR is greater or equal to, what is the infimum of Fx such that A is less or equal to X, less or equal to B. That is the hypothesis. The infimum of this Fx on this whole interval is given by this M. This M. Okay. We name it, we have taken this second. Let this be equation number third. This is third. Next, we develop the relation between this M and this MR. It is obvious. This is less or equal to this, less than this. Equality comes in that case when function is a constant or it repeats its values. Equality also comes. You cannot say strict. So this is this condition. Now we will write the what is the relation between capital MR and capital M. Capital M is the LUV on the whole of F, and capital MR is the LUV, least upper bound or supremum of F on the partition. Just see. Next you have, what is this capital MR? It is equal to supremum of set fx such that x is greater or equal to xr minus 1 less or equal to xr. And this is supremum on the partition, and this will be obviously this MR which is less than or equal to supremum. This is less, look here, fx such that x is a is less or equal to x is less or equal to b. That means on the closed interval AB. And what is the supremum of f on the closed interval AB? It is capital M. So we have developed the relation that capital MR is less or equal to M. This is fourth equation. So from second, third and fourth, what we have got? M is less or equal to M. Okay. Then MR, this MR is greater or equal to small m, and then capital MR is less or equal to M. We have to now combine these. This also means here M is less or equal to small m, this thing. Now we combine this, then this. You see what happens. Our M is less or equal to small mr. I will write it. M is less or equal to M. It is okay. MR is less greater or equal to, and also we did MR is less or equal to capital MR. I have wrote it. It is second equation. Okay. This is actually your first. This is your first. Okay. So M is less or equal to MR. Then MR is less or equal to capital MR. Look here. Then capital MR is less or equal to M. I am combining these. Just combine. Look here. Your M is less or equal to MR. This is this. Your MR is less or equal to capital MR, which is this. And then MR is less or equal to M. This is this. Combining all this, you have got the relation of these. This is the relation. Next we will see. Now multiply just to obtain the lower and upper Riemann sum. What the definition says. Multiply throughout by length of IR. What is length of IR? That is XR minus 1, which is positive. It is delta R. We denote it by delta R, which is positive. Now multiply throughout by length of IR, that is delta suffix R, which is equal to XR minus, it is subscript here, XR minus 1. We multiply both sides, but of course this is a positive because it is length, it is positive. Multiply throughout by this. What is this happens? This is M delta R is less or equal to MR delta R is less or equal to capital M R delta R is less or equal to capital M R delta R is less or equal to capital M delta R, where delta R is XR minus XR minus 1. This is the relation. M times delta R is less or equal to MR delta R is less or equal to capital MR delta R is M times delta R. Okay, I will just see, because we have very cold conditions here in Kashmir. Cold conditions, that is why we are getting a problem in this board. Wait. So multiplying both sides by this delta R, what we get, it is small m xr minus xr minus 1 is less or equal to mr xr minus xr minus 1 is less or equal to capital MR xr minus xr minus 1 is less or equal to capital M xr minus xr minus 1. Now you put r equal to 1, 2, 3, so on to n, adding up vertically. When we add these vertically, what we get? This will be your summation of r running from 1 to n, m xr minus 1. This is less or equal to summation r running from 1 to n, mr xr minus 1. This is less or equal to summation capital MR, similarly xr minus 1. This is less or equal to m summation of m xr minus 1. But this is our, by definition, lower sum. Look the definition. This is the lower sum, mr delta r, and this is upper sum. So you have proved this m has nothing to do with r. You can write this m out. Summation r going from 1 to n, xr minus 1. This is less or equal to, what is this? Sigma r running from 1 to n, small mr delta r, or xr minus 1. Go there, you will see this is lower Riemann sum. L P F comma karke, or L P F X, you may say also that it is less or equal to, this is the upper Riemann sum. Upper, this triangle is a lower triangle that we discussed it there, no need of writing here again. It is UPF or UPFX also, you may say. It is less or equal to, this M has, capital M has nothing to do with this R. This is capital M summation of XR minus 1. Here also it is R running from 1 to n. There also R running from 1 to n. Let us name this equation number A. I will name it A. I will find out this now here. This thing. What is now? Summation R going from 1 to n, XR minus 1. Look, what is this? This is x1 minus x0, then plus x2 minus x1 plus x3 minus x2 plus xn minus 1 minus xn. If you write last but one, that will be xn minus 2 minus xn minus 1. You see what happens? What happens here? This goes with this, this goes with this, and this also goes with this. Only two survive, this and this x0 here survives. This is xn minus 1. This is xn here, xn minus 1. I'm sorry here. This is xn minus 1 here. This is xn. This survives, xn, and this x0 minus x0 survives. All the terms will get cancelled. So you have here two terms survive. It is positive xn minus x naught. Don't get confused here. I am putting or running from 1 to n here, or n. When finally I put n, this is first xn, then xn minus 1. They are here. First xn positive, then minus xn minus 1. Xn minus 1 will get cancelled with this xn minus 1. So what is this? This is your b, this is your a, b minus a. So I have got this thing, summation r running from 1 to n, xr minus 1 as b minus a. Now this b minus a I will be using in capital A. Use b minus a in capital A. Use in capital A. You use this in capital A. So you will get small m times b minus a is less or equal to LPF, is less or equal to UPF, is less or equal to capital M times b minus a. Theorem is proved. This is called the lower Riemann sums and upper Riemann sums remain between m times b minus a. And this is very important when we take the lower integral and upper integrals, lower Riemann integral and upper Riemann integral. There I will quote this theorem again and again because I need their LUB and GLB concept, finding out the lower Riemann integral and upper Riemann integral. For that, this term is very important. Remember this first law of mean. I will write final setup here for this. So when we use this in A, what we have proved? We have proved now, using in A, we have proved m times b minus a is less or equal to LPF, lower Riemann sum. It is less or equal to UPF is less or equal to capital M times b minus a. And remember, this small m is the GLB on whole interval AB of F, and this is the capital M as LUB of whole interval on this, and P is any partition. This is the lower Riemann sum and upper Riemann sum lie between this. We have very important observation. Theorem is proved. Theorem is proved. Theorem is proved. Now we have important observation. This is important observation that you will remember. It is this. Above theorem being true for any partition of P on closed interval AB, or in mathematical language we will say P belongs to the family of partitions of closed interval AB. It is true for every partition. So this implies set of whatever you partition you take, P1, P2, P3, you will form a set of lower Riemann sums. For partition P1, for partition P2, for partition P3, you will form a set of lower Riemann sums. Similarly, a set of upper Riemann sums. So set of lower Riemann sums. What is that? This set LPF, such that P is any partition of closed interval AB, and दूसरा set B, and set of upper Riemann sums, that is UPF, such that P is any partition of closed interval AB. ये lower Riemann sums और upper Riemann sums, P1 लीजिए, P2 लीजिए, P3 लीजिए, ये लाई करता है between this and caught between this. कोई भी वैल्यू दीजिए P1 का, इसका मतलब है कि इन lower sums और upper sums का minimum भी है, they are caught between minimum and maximum, between LUB and GLB. So they are, according this theorem tells us that P को कोई भी वैल्यू दीजिए, यही हमने लिखा, set up all the lower Riemann sums, set up all the upper Riemann sums remain bounded. They also remain bounded. It is a very important this observation that you may take it in this objective type question also. When you have F bounded on the closed interval AB, then what happens? It is bounded on each subinterval of the closed interval AB. Then again, it also remains bounded. The lower Riemann sums and upper Riemann sums also remain bounded on the closed interval AB. Remain bounded. You may say here that this M times B minus A is GLB, and capital M times B minus A is what? LUB, maximum. This is minimum and this is maximum. Capital M B minus A means the LUB supremum, and small m times B minus A remains the GLB, because lower Riemann sums and upper Riemann sums are caught between the minimum and maximum. This is very important, and you just probe this result fully. But before probing it, go to previous lecture. That will help you to understand lower Riemann sum and upper Riemann sum. Thank you very much. We will be meeting next, and I finally request you to enhance your logical thinking and critical thinking by this reading math more and more. Thank you very much.